Yeah. So the dy dz, this is fixed. This is constant because when the fluid flows around along this direction, the area is not changing. Dy dz. So only dx dt, that is the velocity u. So therefore the rate of change of mass is density into area into the velocity. Now we use this formula as the rate of change of mass. So what will be the mass flow per unit time or rate of change of mass at the first case? So the rate of mass flow at the first case. So this will be the rho is the density, velocity. Now we need the area. So how to find the area? Suppose we assume that is the flat plate, okay, and that flat plate has some breadth or width. Suppose we denoted the width as d, okay. So the d be the width of that particular plate on which the fluid is flowing, and this is the y direction. Suppose the increment is dy, okay. So this is d into dy. Now this is only for the small increment. Now if we need the for entire length, so then we have to integrate it with respect to 0 to delta. How delta? Because the thickness of this boundary layer is delta. So we make it 1. Now we draw another figure like this, or now we see that in the first case the mass flow rate will be higher than the second case, because in the second case, due to the internal friction, the velocity is reducing, so the rate of mass flow is also reducing. So to get the same mass flow rate in the first case, what we need? So you see the formula for our mass flow rate is that density into area into velocity, okay. Now what is our main aim? Our main aim is to get the same mass flow rate in the first figure. In this case we make it case 2. So for that, you see, if you need the same mass flow rate, the velocity in the second case is capital U. Okay, second case means this case. Velocity in the second case is capital U. So capital U is greater than your small u. So to get the same mass flow rate as your case 1, either you have to reduce your rho or you have to reduce your area. But you cannot reduce your rho because you don't have any control over rho, because rho is the incompressible fluid. This is fixed for a particular fluid. Again you come to the area. What is the formula for area? Area will be this particular width into that particular height. Now width of the surface is fixed because you are taking the same surface. Only possibility is that you can reduce the height. Okay, so what we do, we reduce the height by some length delta 1. Okay, we are reducing the height. Why? Because we have our main aim is to get the same mass flow rate with our case 1. Okay, so after reducing the height, the rate of mass flow is, okay, so density is rho, velocity is u. Now what is that particular length? It will be the total length is same in both the cases. So delta minus delta 1, because you need only this part, only this part. So this total length is delta into the thickness d. So as per our assumption, now the mass flow in case 1 and case 2 are same. So therefore, rho u delta minus delta 1 into d will be equal to 0 to delta rho u d dy. So now this d is same because this is independent with respect to y. Rho is cancelled because the fluid is incompressible, so rho is constant. So this implies delta minus delta 1 will be 0 to delta small u by capital U dy, as capital U is independent of y. So this implies delta 1. Delta 1 is our displacement thickness, because you are displacing the potential flow upward. Displacement thickness, okay, it will be delta minus 0 to delta small u by capital U. Now this first term can be written as, yes, this is possible. If you integrate your 1 with respect to y, and after substituting the limit, you are getting the previous line. So this is 0 to delta 1 minus small u by capital. So this is the expression for your displacement thickness. So till now you study this one, you clarify if there is any doubts. In the afternoon I will give another two thicknesses, as is the momentum thickness and the kinetic energy thickness, based on this particular theory. Okay, so till now, have a good time.